Okay, so today we're going to talk about integration by substitution from calculus. And let's look at some examples. So let's say we have the following. Say we want to take the integral of x over the square root of x squared plus 1 dx. For my substitution, I've got my eye on this inside function, right? If you think about composition of functions, this is the innermost function. That at least tells me I should consider that for a substitution. It's not always going to be that, but it's a good thing to at least consider. So I'm going to let u equal this inside function, x squared plus 1. I'm going to carefully take the derivative, so that's going to give me 2x dx. This gives me confirmation that this was a good choice because this portion right here will help me get rid of this and write it in terms of my new variable. I want to turn all of this x stuff into u stuff in a sense. So yeah, this choice is good because this helps me with this. And then this helps me write this in terms of u. Okay, so I'm going to just isolate this so it looks identically like this. So this is my substitution. And there's going to be a rule that we're going to need in a moment. So I'm just going to say recall. So you want to be on the lookout for this. So recall the following. So if n's not equal to minus 1, then we have the following. So then the integral of x to the n dx is equal to x to the n plus 1 over n plus 1 plus c. That's the power rule for integration, right? So you increase the power by 1 and you divide by that same new power increase. Okay, so let's carry through with this first and then see if it puts us in a position to solve the problem using this. Well, x dx, what are we going to call that? So x dx is exactly this, right? So let's replace this with this. So that's going to give me 1/2 of du. This is over the square root of, well, we're calling that u, right? So that's the square root of u. Remember, with constant multiples, we can factor this in front of the integral. And this we can bring up to the numerator using negative exponents. So I can call that u to the minus 1/2 du. And now we're in a position to use this. So n is not equal to minus 1, therefore, yeah, I can go ahead and use that. So we're going to increase the power by 1, and then we can divide by that new power increase. Okay, the 1/2s will cancel. That'll leave me with the square root of u. And then remember, if we're dealing with an indefinite integral, an integral with no bounds like we are here, if we start with variable x, we need to end with variable x by doing a back substitution. So I end up with the following. So this is the square root of x squared plus 1 plus c. And I do want to give you a little warning. Some students will want to call this x plus 1, but in general, we can't take the square root over plus or minus. Okay, so do be careful. All right, so with that said, let's go ahead and try another one. Feel free to pause here if you need to. Okay, so let's try this. Let's say we've got the following. So let's say we've got the integral quantity ln of x to the 7th all over x dx. Now, if you're a little bit confused by this, remember you can always rewrite that, right? So if this is bothering you, just realize that this means the same thing as this. Right, I can always write this divided by x as times the reciprocal of x. That's perfectly fine. And maybe this is a bit more suggestive in technique compared to this, right? Because I noticed that the derivative of ln is 1 over x. So maybe for my substitution, it might be smart to try the natural log of x as u, and the derivative of this is exactly 1 over x dx. This gives me confirmation that this was a good choice, because here my derivative helps me get rid of this and write it in terms of my new substitution variable u. So what do we have? We have exactly this, which of course you can write as that, is perfectly fine. This is equal to, well, think about this. This is u to the 7th. This is exactly what we're calling u. So that's u to the 7th. And then this right here, which really is 1 over x dx, that's what we're calling du. But this is exactly our power rule from before. So we know to increase the power by 1 and divide by that new power increase. Don't forget your plus c. And then we're going to back substitute, right? So this is exactly u. So we're going to plug this back in for u. And we get ln of x to the 8th over 8 plus c. Now, of course, you could check this. You could compute the derivative carefully using the chain rule, and you should land back here at the integrand. Okay, so yeah, let's go ahead and try another one. So here we've got the integral of e to the secant of x times secant of x times tangent of x dx. So it looks really involved, but let's just recall some things. So let's recall that, well, the derivative of secant of x is exactly that product of secant and tangent. So that'd be secant of x times the tangent of x. So that's very suggestive of a technique, right? So we should do substitution. I mean, if I let this be u, then du will help me get rid of all of this. So that was good. So u is going to be, in particular, this secant of x, right? So u is going to be secant of x. Now, the derivative of secant, we said, is exactly secant of x times tangent of x dx. And this will help me get rid of this. So we should call this du. So that means that this is equal to, well, this is what we're calling u. And this is what we're calling du. And so this was really helpful because the antiderivative of e to the u is itself. And then we can just go ahead and back substitute